chapter, and the title is Enthalpies of Reaction from Standard Heats of Formation. But I'm hoping to convince you when we're done that we are just doing Hess's Law again. Right? We do need a couple definitions, and then we're going to be doing Hess's Law. It's called Enthalpies of Reaction. It's going to look like this: enthalpy, or the change in enthalpy of a reaction, right? Well, I guess a reaction is a change. So there's the enthalpy of reaction. And then we're going to get this from the standard heats of formation. Okay? So let's get some definitions in here. So first of all, a standard state. So a standard state, and what is meant by the term standard state? So for a gas, the standard state is the standard state of the gas is the pure gas at 1 atmosphere exactly. All right? That's the standard state of a gas. The standard state of a liquid or a solid is the liquid or solid is the form of the pure substance I'm reading this out of the book, okay? This is on page 247. Page 247. The form of the pure substance in its most stable form, which is a liquid or solid, at 1 atmosphere, right? Look familiar? At 1 atmosphere and at the temperature of interest, which is usually 25 degrees Celsius, okay? Which is roughly room temperature. It's basically where we live, okay? 25 degrees Celsius. So, for example, bromine in a standard state is going to be a liquid. It's one of the very few, or rather bromine, right? Molecular bromine. One of the very few that's a liquid. Mercury, I guess, is the other one, right? In its standard state is going to be a liquid. Hydrogen in its standard state is going to be a gas, right? Oxygen in its standard state is going to be a gas. Oh, and its standard state is going to be 1 atmosphere, right? 1 atmosphere. 1 atmosphere. Carbon in its standard state is going to be a solid, right? Okay, so that's what we mean by standard state. One last thing that I don't have here, I'm going to make myself some space here, and that is, it's in your book, also says the standard state of a substance in solution. What is meant by that? In solution. Usually that's going to be aqueous, okay? So let's take sodium chloride, aqueous. The standard state of sodium chloride is going to be a concentration, that means concentration of sodium chloride is equal to 1 molar, right? That's the standard state, 1 molar, right? So you just have to be watch out for that word standards, or that term standard state, and all of those things which I just told you. You can assume, or you have to assume actually. Okay. So now a standard enthalpy, and this is probably standard is probably the biggest term in this section. Standard. What does standard mean? Oftentimes we're going to have a little circle when we're talking about standards. Okay. So a standard enthalpy change is going to be the the standard enthalpy change is the enthalpy of a reaction when everything is in its standard state. Everything in standard state. Okay, that is all the products and reactants. So you've got A plus B produces C. Maybe has some change in enthalpy of a reaction, right? Well, this will be called a standard enthalpy of a reaction if all of these guys are in their standard state. Okay, this will make more sense as we do some problems. So, and again, I'm just reading this from your book. This is on page 247. Okay. Now, the standard enthalpy formation. Okay, standard enthalpy of formation, and that means that you get the standard enthalpy of formation is when you have is the change in enthalpy when 1 mole of compound is formed from its elements in their standard states. Okay? So, what's the standard enthalpy formation going to be of oxygen? Well, it's going to be 0, right? The standard enthalpy of formation is going to be 0, right? Because it comes from oxygen in its standard state, right? We'll do more examples in a minute, but really, okay, so the other rule that's given to you on page 247 is that the standard enthalpy formation of all pure elements is 0, for the reasons which I just showed you there. All right, let's look at the table first. So, can you see that the standard enthalpy formation of bromine as a liquid? Can you see this? I know this is too small to see. All right, so I'm on page. What page is this table on? You need to go to page 248. This is way too small to see. 248, and look at this table. It's table 6.5. Well, it's 0. Why? Because bromine is already in its standard state. What about calcium? In its standard state is 0. But if we're going to make calcium oxide, then its standard heat of formation would be minus 634. What would that look like? Well, calcium oxide would be coming from calcium plus oxygen. Now, it's 1 mole. The definition is 1 mole, so this is going to have to be 1/2. Okay? So this would be the reaction that has an enthalpy of, can you see that? All right. This is getting a little bit busy, but I don't think I want to do any other of these examples for you. It's to me just repetitious. But all right, have a look at that table on page 248. So let's look at a particular example, and this will make more sense. Write equations for the formation of magnesium carbonate solid and what's this, glucose, from their respective elements in their standard states, and include the value of the standard heat of formation for each equation. All right, so first of all, let's do A over here, okay? Magnesium carbonate is going to be coming from magnesium. Its standard state is 0. It is solid, and carbon, its standard state is solid, and oxygen, its standard state is a gas, right? So it looks like it's going to be 3 halves, right? Because there's 3 of them here, and only 1 of those and 1 of those. So this is the answer for the equation for the formation of magnesium carbonate, and that's it. This is the formation of magnesium carbonate from its elements in their standard states. From its elements in their standard states. Now let's look up the standard heat of formation. Say it out loud. Standard heat of formation in the previous table on page 248. I'm looking at it right now, and I see magnesium carbonate. Come on. Oh. Just a second here. I'm looking. It's not here on this page. Son of a gun. All right, poor planning. Not here on this page. I'm going to have to look it up. I'm going to Google it. I'm going to Google that right now. Google. What is the standard heat of formation of magnesium carbonate? Spelled magnesium carbonate wrong, apparently. What is the standard heat of formation of magnesium carbonate? All right, NIST web book. Standard heat of formation. Wow, this is not as pretty. There's the standard heat of formation. It looks like it's minus 111. Can you see it right here? Standard heat of formation of magnesium carbonate is minus 111.69 kilojoules per mole. Okay. I gotta go back to my PowerPoint. I've lost my notes there. But I'm gonna do them again because I'm really good at this. I know you're impressed. Okay, A, it's gonna be magnesium in its standard state plus carbon in its standard state, which is solid, plus oxygen in its standard state, which is gas, molecular gas, right? It's going to give me magnesium carbonate. And its standard heat of formation is equal to minus 1111.69 kilojoules per mole. My phone rings, but I can't answer it because it's broken. So what I have to do is I gotta hang up on the person because I can't see it. Then if it's working good enough, I can flip through there and see. It was my son, and I'm going to call him back. He will happily understand he's safe. In case you're worried about me not taking a phone call from my son, I can tell you I'm sure he's safe. All right, so let's do glucose now. And that's, well, carbon, right? Again, carbon in its standard state is a solid. Oops, I forgot to make this 3 halves. Sorry, right? Remember that? There's 3 of them. Oh, okay. Carbon plus hydrogen. What's hydrogen's standard state? Gas. I'm a little bit impatient right now. And O2, gas, is going to give me C6H12O6 and a solid. Okay? So there's the formula for it. Now, it looks like it's going to be 6 of these, and 6 of these, and 3 of these, right? C6H12O6. Okay, so there's it. That's the reaction. Now, I'm going to look up the standard heat of formation in the table, and it is there, like it's supposed to be. And that is, did I overlook magnesium carbonate? I did not. I don't even see it there. I can't believe that. All right, I'm looking back to glucose now. It looks like it's the standard heat of formation from the table on page 248 is equal to minus 1273.3. I really should have insisted that you pause the video and look that up yourself. All right, I'm stealing from you. Okay, it's all right. We've got another example here. Okay, so use the standard enthalpy of formation to determine the standard heat of reaction for this reaction. All right. Uh-oh. This is going to be scary to some people. All right, so what I'm going to do is I'm going to write out the standard heats of formation for everything here. There may be some overlap in what I'm right. I'm going to do ammonia. Oxygen I'm not going to do because right I know what that is. That's 0. Let's do it. No, I can't. I just can't do it. Okay. So ammonia, right? And I know that's 0 because it's not. It's nil by itself. Nitric oxide and water, right? So this is going to come from nitrogen, which is a gas, and hydrogen, which is a gas. So it looks like it's going to be 1/2 of this, and what is this? 3/2, right? This is N2 plus O2. Looks like this is going to be 1/2 and 1/2. And this is, what is this? H2 plus O2. This is going to be 1/2. Okay, so I've got my 3 reactions here. And I know my standard heat of formation, the change in enthalpy of this reaction is equal to the standard heat of formation, right? Because I defined it like that, which is the standard heat of formation of ammonia. You need to pause the video and look these up. Please do that right now. It's gonna be so much. This video is gonna be so much more valuable to you if you do that. Okay, so ammonia is minus 45.9. These are all going to be in kilojoules per mole. Nitric oxide is 91.3. And water, and what was this? Water as a gas, okay? Water is what? Where is water in here? Don't tell me. See, there it is. Okay, minus 241.8. Minus 241.8. Now what I've got to do is I got to figure out how I arrange these guys together to make them. I'm going to do Hess's law. By the way, Tro gives an alternate suggestion here on how to do this. It's probably not a bad idea. It's probably not a bad idea. In another video or on request, I'll walk you through how he does it. But I like having fewer tools and just be able to be good at them. Okay, so it looks like this is going to be. You see what I'm remember what I did before? 6. So I'm going to take this and multiply by 6. Okay. Nitric oxide. It's a product, and that's a product there, so I'm going to have to multiply that by 4. And ammonia, this is a product here, it's a reactant here, so this is going to have to be multiplied by negative 4. All right? Okay, now I'm going to rewrite these equations, okay? I'm going to rewrite the first one. So minus 4, I'm going to first of all turn everything around. This is going to become 4 ammonia. See what I did here? I turned it around and made it negative. Produces 4, that's 2 and 2. And then negative 4 times that is 6, right? Because 4 times 3 is 12 divided by 2 is 6. Plus 6 H2. And the enthalpy of this reaction is going to be negative 4 times that. Right? I'm going to do that real quickly before I move on. 45.9 minus 4 times 45.9 gives 183.6. And this is in kilojoules per mole. Everything in this column is, okay? All right, so we've taken care of that one. I'm going to get rid of that. Now, what's the next one? 4 times that. Aha, okay, so that's 4 times 1/2 is 4 and 2, right? 4 times that is 2. O2, okay, gives 4 NO. And so the enthalpy of this reaction is going to be what? 4 times 91.3. 4 times 91.3 is equal to 365.2. Okay, and now we've taken care of that one. All right, now what I have here, 6 H2s. 6 H2s plus 3 O2s, right, gives 6 waters. Okay, taking care of that one. And I multiplied that by 6. So the enthalpy of that reaction is going to be, can't do that in my head, 6 times 241.8 equals negative 1450.8 minus 1450.8. Okay? Now I want to prove to myself, let's go back to a different color. Let's go back to red. Okay? Now I want to prove to myself that these sum, which I'm assuming they do, right? Because this always works out. I assume it always works out, right? I'm going to prove to myself it gives me this, right? So watch this. 4NH3 plus 5O2 produces 4 nitric oxide plus 6 waters, okay? So we're going to go through here, and we're going to go, I'm just going to go from the top. I don't know why I typically start here from the left. I don't know, let's do this. Ammonia. So this is here, right? Taking care of that. N2 is nowhere here, but look at this. Watch. Boom. Ooh, those don't cross off. What happened here? Did I make a mistake? That's 2 N2s. Ah, I made a mistake. Look at that. This is not supposed to be 4. It's supposed to be 2. Do you see that? Okay. It's supposed to be 2. And they do cross off. Okay. Yeah, things don't cross off. See that? What's matched up with that. Remember I did that in the last one? It's going to get kind of busy, all right? Okay, my H2s. Okay, well, there's no H2s down here, but aha, they cross off with those. Right? See that? Okay, those cross off. Products in one, reactants in the other. Aha, okay. Now, I'm going from here to here to here, taking care of. Oxygens. Okay. Ooh, I have 5 oxygens down here, and there's 5 here. Right? You see them? They're there. Taking care of that. Okay, here's my 4NO. They're here. Boom. Taking care of that. And my 6 waters. Okay. They're here, and I'm taking care of that. Exactly. So, I made these reactions from these up here so that if I just added everything, it would give me this. And it worked. Okay? Now, I'm just going to add these guys up because I took these, did the same thing to the enthalpies that I did to the reactions themselves. And so the change in enthalpy of the reaction is going to equal the sum of all those things. Okay, so what I'm going to do is I'm going to take the minus 1450, and I'm going to add 183.6, and I'm going to add 365.2. Okay, and I get minus 902. Wow. Genius. Look at that. Isn't that cool? Minus 902 kilojoules per mole. And that is my answer. That is the standard heat of the reaction. And I know it because I did all my standard heats of formation here. Okay? And then I added them together by Hess's law. Okay? All right. Let's see. I think there's one more example here. Yep. Okay, so a city of a bunch of people uses a lot of energy per day. Suppose all this energy comes from the combustion of liquid octane. So before I do anything, let's identify what that means. Combustion of liquid octane. So that's H18 plus oxygen gives me carbon dioxide plus water. Okay? And use the standard enthalpies of formation to calculate that. We'll do exactly what we did in the previous question. Okay? Except this time we had to interpret that. All right, but this is not balanced yet, so let's balance this real quickly here. 8 here. This must be 8. 18 here. This must be 9. Now, how many oxygens do I have? I've got 9 plus 16, 25. This is going to be 25 over 2. Okay. All right. Now, look at this is the standard. This is asking for the standard. Okay. So that means 1 mole. So I'm going to leave this as 25 over 2 and 8 and 9, right? Because this is the standard enthalpy of reaction for the combustion of octane. All right, so let's leave it like that. And let's now say to ourselves, let's think about this is all going to come from the standard heats of formation. So my first reaction, I think I've already gone to black, haven't I, is going to be C8H18. And that comes from its elements. Left myself too much space over here, right? That's a solid in its standard state. And this is a diatomic molecule in its standard state. It's going to take 9 of those, right? And 8 of those. Okay, so that's reaction number 1. We'll look up the standard heat of formation. Actually, I'll do that right now. Page 248 probably, right? Of octane. It's not there. I have to Google it. Where? looking in the textbook on that, okay? Oh, it's in the appendix 2B. It's in the appendix 2B. Or 11B, I guess. Okay. So I'm gonna write it down though here. It's minus 250.1. Okay, that's the standard heat information of this guy. Okay, oxygen has no standard heat information because it's a pure element. It's going to be 0. Carbon dioxide, it's going to come from its elements in its standard state, which is carbon and O2, right? Looks like that's already balanced as it's written. The standard heat information of carbon dioxide, looking it up in the textbook right now, is minus 393.5. Okay, and so I get that one, and now we need water. And the standard heat information of water is, this comes from H2 plus O2, right? And that's going to be, I guess, 1/2. We just did water a second ago. Now this is water as a gas, okay? You know, oh, gaseous water. Oh, good. I'm so glad I said that because I was afraid that you wouldn't necessarily know, okay? Gaseous water. And so gaseous water is minus 241.8. Minus 241.8. Okay? Can you read my writing? All right, now what I got to do, you've seen me. I just did this in the previous question. I'm going to rearrange these so that they're going to give me this, right? Well, this first one is backwards, right? Because it's a product here and it's a reactant up here. So I have to take that and multiply it by -1. So I'm going to shift this over a little bit. I just don't have enough room over there. C8H18 produces 8 carbons plus 9, right? This is just rewritten. So this is going to be this times -1. The heat of this reaction is going to be 250.1, okay? Now let's take the next one, carbon dioxide. So it looks like I'm going to need 8 carbon dioxides to go with that. So I'm going to say 8 carbons plus 8 O2 produces 8 carbon dioxides, right? So I'm going to multiply that by 8. I can't do that in my head, but I've got a good calculator here. So it is 8 times 393.5 minus. So this looks like this is minus 3148. Okay, kilojoules per mole. Let me just, I'm going to go a little slower this time because I made a mistake last time. I have to, when things don't work out in a Hess's law, you sort of know to look at it. But all right, so that's good. Now this is waters. Looks like there's 9 waters here. See it? 9 waters, and so the waters are going to be that times 9. Right? So it's going to be 9 halves H2 plus 9 O2 produces 9 waters. Okay. What's the standard heat information of this? It was just that times 9. 9 times 241.8 gives 2176.2 minus 2176.2. Okay. Now, I didn't leave myself enough space here, did I? But look at this. When I add these all up, I'm missing some oxygens. I got to go back and see what's going on here. So it's 25 halves, right? But here I have 7. What's 25 halves? 13 and a half? Well, let's try to figure it out. I'm gonna go the long way, okay? So this, if I add all these guys up, so I'm aiming for this reaction here, right? So it's C8, 8H18. Okay, so that's taken care of. My 8 carbons cross off. Ah, these do not cross off. Right? So it looks like I'm going to have to do more there. I got a mistake here somewhere, don't I? Because you see what happens is, right, this 9, there's no hydrogens up here. Right? And I've got 9 hydrogens here, and so only some of them cross off. So what is the problem here? Well, let's keep going. Let's go with, we'll do hydrogens last. Let's come here and say carbon dioxides. 8CO, those are taken care of, okay? And that's what I wanted, 8 carbon dioxides. And I want 9 waters, that's good. Nine waters. Okay. And my oxygens and hydrogens simply don't cancel. Gives me 17 oxygens. Did I balance this wrong up here? Let's see, there's 16 here, 16 oxygens. Yeah, I balanced this wrong. That's my problem right here. Look at that. This is not 25 halves. This is 16 plus 9. It's just 25. Oh, yeah. It is 25 halves of oxygens. Something's not adding up here. Wow, but you can find it. Okay, I'm going to take a break and come back to this because I've got a mistake here somewhere and I don't see it. All right, so I'm going to take a break and come back to it. I'll see you in a... Okay, so I went and got a drink of water and came back and looked at it afresh, and I see the mistake. So I don't have, the way that I do my my videos, I don't have a way to save that ink on that slide. So what I did was I took a screenshot of it, and I'm going to show you where the mistake was, okay? So here's my screenshot. Should have that ready. Screenshot shows this is what the video looked like, okay? Or what the screen looked like. And what I did was, can you see that I put 1/2 H2 plus O2? This equation is not balanced. That's not balanced. Okay, so there's a mistake here. That equation is not balanced. Can you see it? So this was a problem, and if I had this on a test, you see, I would get down to the end, things don't make sense, and I go back and check it, like I did here. Okay? That's the nice thing about doing Hess's law. If they don't make sense, you see it. And folks, both times I made a mistake with these equations and caught it because I was using Hess's law. All right, so this one took me a little extra time. I couldn't just go back and glance at it. I had to go and think for a minute. But anyway, I'm back, and so let's go back. I need to reset it up, though. I'm sorry to say, because I don't have a way of saving that. So let's reset it up this time a little more well correctly. Okay. So first of all, we know we're doing. There's actually two parts to this, right? Because ultimately we're going to have to find out how many kilograms of octane to provide a certain amount of energy. So I'm going to divide this page up into two sides so I don't have to go back and forth. All right, and let's come over here and let's say we're looking for C8, H8. It's the combustion of octane, right? So that's plus oxygen gives carbon dioxide plus water. And black, this is going to be 8. That's going to be 8. There's 18. This is going to be 9. And there's 16 oxygens over here. Can you see it? 8 times 2 is 16, plus 9, 25. So this is going to be 25 over 2. I'm sorry, my writing's so small, probably can't see it from where you're sitting. Okay, 25 over 2. Balance that yourself and you'll be able to figure it out, okay? So now we're going to do this from the standard heats of formation of these guys. So first of all, I'm going to write the standard heat of formation. Man, I have no way of erasing this. How can I make that something correct? Okay, let's. I can't. C8H18 comes from. Okay, we'll get that in a second. Oxygen is already in the standard state. That's going to be 0. Carbon dioxide comes from, right, and water comes from, right? So octane comes from carbon plus H2. Carbon dioxide comes from carbon and oxygen. And water comes from hydrogen and oxygen. Now let's balance these out. There's going to be 8 of these and 9 of these. Okay. 1 and 1 of those. And this is where I got it wrong last time. I put a 1/2 in front of the hydrogen, which is not right. I do need H2s. It's the 1/2 goes right here. Aha. Okay. So those are my reactions for the standard heats of formation. Okay. And I didn't write those down. The standard heats of formation of octane is minus 250.1. Standard heat formation of carbon dioxide is minus 393.5. And of water, it's minus 241.8. Okay? So, in order to turn these equations into that one, I'm going to go a little faster this time. All right? I'm going to have this 9 water, so I'm going to multiply that by 9 because it's a product, and that's a product. Carbon dioxide, see, there's 8 of those. Okay? And this is 1, but it's backwards, so it's going to be minus 1. Because I'm going to encourage you, I'm not going to do this right now. I did it in the previous slide. This part I did correctly. This times that. Multiply that by minus 1 and fill it out, okay? Take this one, multiply by 8, right? And take this one, multiply by 9, okay? And then add them all up. After you've done that, add them all up and see that they, in fact, do go to C8, H18 plus 25 over 2 oxygens. Sorry about the text there. Plus 8 carbon dioxides plus 9 waters. That's what they're going to come to. Okay? So I'm going to take this number and multiply it by negative 1. It becomes 250.1. This I'm going to multiply by 8. Did on the previous slide. I still have on my computer, actually, in my calculator. I've got that times 241 is just 2,176.2, and it's going to be negative because it's times 9, right? 9 times 241 is going to give me that. And then 8 times 393.5 is going to give me, oops, can't do that, just me. 3148, okay, minus 3148. And so the standard heat of this reaction is going to be minus 3148, positive 250.1, minus 2176.2. It's going to be minus 5,000. Okay? Minus 5,000. Minus 5074.1 kilojoules per mole. Okay? Now, if we want to know the kilograms of octane, then what we need to know is, watch this, it's going to be kilograms of octane. I'm just going to, I don't want to put I don't want to spell out the octane there, okay? Kilograms per gram. Grams per mole. Moles per kilojoule. Kilojoules, that's it. We're kind of fast with that one, okay? So it's 1 times 10 to the 11th kilojoules times minus 5074.1 kilojoules per mole, right? So that's on the bottom. Can you see that? And the grams per mole, oops, didn't do that. 8 times 1201 plus 18 times 1.008 is equal to I can't do that in my head. Just a minute here. Okay. Clear. Sorry. 8 times 12.01 plus 18 times 1.008 equals 114.224. Okay, so that's going to be 114.224, and then there's 1,000 grams per kilogram, right? That's going to equal our answer. There's our answer right there. So let's do it on our calculator, okay? 1 times 10 to the 11th divided by 5,000 right, times 114.224 divided by 1,000. Okay, so it looks like it's going to be 2 million. Is that right? 2 million. This answer here then is going to be 2.251 times 10 to the 6 kilograms of octane. Okay, I think he's saying that that's a lot of gas. Okay, long problem. Nice long problem. Lots of steps that were accessible to us. This is its own problem, right? In what was that? That's his own problem in chapter 3, I guess, right? And then this is Hess's law, which is section 6.8, Hess's law. Okay. Hope that's helpful.